So it's time now, we can start. Good evening, friends. So we are very happy to have with us today a very distinguished mathematician and theoretical physicist, Professor Jürg Fröhlich from ETH Zurich, and he will deliver this year's 13th OSMU lecture on the subject of a theory of quantum jumps. Jürg was born in Switzerland, and in 1965 he began to study mathematics and physics at ETH Zurich. He obtained his diploma and PhD from there, and subsequently was a postdoc at the University of Geneva and at Harvard before taking up an assistant professorship in the maths department of Princeton University in 1974. From 78 to 82, Jürg was a professor at IHES Paris, and since 1982, he has been a professor for theoretical physics at ETH, where he founded the Center for Theoretical Studies. Over the course of his career, Professor Fröhlich has worked on quantum field theory, including axiomatic quantum field theory, conformal field theory, and topological quantum field theory, and on the precise mathematical formulation of models of statistical mechanics and theories of phase transitions, as well as the fractional quantum Hall effect and non-commutative geometry. He is best known for introducing rigorous techniques for the analysis of statistical mechanics models, in particular continuous symmetry breaking, and for pioneering the study of topological phases of matter using low-energy effective field theories. Professor Fröhlich has received numerous awards, including the Danny Heinemann Prize, the Max Planck Medal, and the Henry Poincaré Prize. He's a member of the Academia Europa, the Berlin Brandenburg Academy of Sciences and Humanities, a fellow of the American Mathematical Society, and an international member of the National Academy of Sciences. In 1978, Professor Fröhlich gave an invited address to the International Congress of Mathematicians in Helsinki, and in 1994, he gave the plenary talk of the ICM in Zurich. It's a pleasure to have you with us, sir. Please take over.
Thank you for your introduction. So this is about quantum theory. I think it's a somewhat new approach to some of the well-known problems of quantum mechanics, and I'm trying to go into to sketch my views on these matters. So here is a table of contents. I will very briefly sketch what I call the ETH approach to quantum mechanics, which will then be illustrated on concrete examples. I will introduce these examples. They are non-relativistic models of matter interacting with the quantized radiation field. Then, in the sense of a simple analogy, I will discuss the theory of diffusion and the associated theory of simple random walks on a lattice. Then I'm going to consider the Lindblad dynamics that comes out of the ETH approach when applied to the models I have introduced in section 2, and how the Lindblad dynamics yields a somewhat novel stochastic process that I will describe, and then I will look to conclude at a very simple example of two-level atoms and talk a little about fluorescence. I have profited from many discussions with various people, some of whom I collaborated with, and they are mentioned here. So here is the abstract. I think the most important part of the abstract is this quote of Heisenberg. The constant element in physics since Newton is not the configuration or a geometrical form, but the law of dynamics. The confusions in the foundations of quantum mechanics come, I think, have their origin in people not knowing what the correct law of dynamics of states is in quantum mechanics. And in this talk, I describe a specific law of dynamics for non-relativistic quantum mechanics. The relativistic case is interesting too, and I could talk about it, but certainly not all of it in 1 hour. That's impossible. So the time evolution of physical systems consisting of charged matter interacting with the quantized electromagnetic field, electrons in the shell of an atom, for example, coupled to the radiation field. This time evolution is non-linear, dissipative, and stochastic. It features isolated random events, sometimes called quantum jumps. And what we have to do is to search for the equations describing this evolution. Explicit such equations can be found in idealized descriptions of the systems of matter interacting with the radiation field, and they involve this new type of stochastic buses, which I call a quantum Poisson jump buses. So here is a sketch of the ETH approach to quantum mechanics. In quantum mechanics, the time evolution of averages of states taken over a large ensemble of identically prepared physical systems is linear and deterministic. The solution is described by a Schrödinger von Neumann equation or by a Limplot type equation. However, the quantum mechanical time evolution of the state of an individual physical system is non-linear and stochastic. And we have to find the law that describes it. So a conceptual explanation of this fundamental fact is the core of the ETH approach to quantum mechanics, special case of which appropriate for precise of non-relativistic quantum mechanics is now sketched. It is based on the following four ingredients: physical quantities of a system, for example, the energy, the number of particles in a certain region of physical space, etc. Such quantities are represented by abstract self of such operators. At that time T, all the elements family are mapped in OS is mapped to a concrete operator X of T, itself a joint, and it acts on the Hilbert space H of the system. The time evolution of these operators X of T is given by the usual Heisenberg equations. Then, point 2, I introduce algebras of potential events, which are defined as follows. The algebra E greater or equal to T is the one that is generated by all the operators X of T prime. X of T prime represents some physical quantity X hat in OS, and T prime is greater or equal to T. So you take, finite linear combinations of finite products of such operators, all localized at times greater or equal to T, and then you close what you get in either in the norm, in the operator norm, or in the weak operator topology. The weak operator topology has certain advantages, so I usually assume it's weakly closed. It follows right from this definition that the algebra E greater or equal to T prime is contained in or equal to the algebra E greater or equal to T whenever time T prime is larger than time T. And the Heisenberg equations imply that all these algebras are isomorphic to one another, the isomorphism being provided by the propagator of the system. H sub S is the Hamiltonian of the system. I assume the system is autonomous for simplicity. So in particular, all the algebras E greater or equal to T are isomorphic to the algebra E greater or equal to 0 for all times T. What are potential events or potentialities in quantum mechanics? These are partitions of unity by disjoint orthogonal projections. These disjoint orthogonal projections represent alternatives, if you like, and they act on the Hilbert space H of the system. A potentiality that might happen at the time greater or equal to T has the property that the projections in this partition of unity, the pi sub xi's, are contained in the algebra E greater or equal to T. Now comes a very important idea, which, as far as I know, has been missed for a long time, but I think it's a basic idea about quantum theory. An isolated but open system S is characterized by the property that it satisfies what I call the principle of diminishing or declining potentialities, which says that the algebra E greater or equal to T prime is contained in, but not equal to the algebra E greater or equal to T, whenever time T prime is larger than time T. So in other words, these algebras E greater or equal to T are properly embedded into one another, and they become smaller and smaller as time T increases. So that's a principle, and of course we will have to find out whether this principle, is satisfied by concrete examples, and that will be explained in the talk. Then what is a state of a system? A state of a system at time t is a normalized positive linear functional. In other words, a state in the usual sense of the word, but only on the algebra E greater or equal to T, because we want to make predictions about the future after time t. So the state has to be a state on the algebra E greater or equal to T. If these algebras were independent of time t, as it is the case for closed systems, relativistic systems with a strictly positive mass gap, then in the Heisenberg picture, states would be independent of time t. They would only depend on time t in the Schrödinger picture. But if the principle of diminishing potentiality holds, as it should for an isolated but open system, then the states will depend non-trivially on time t. And this is a consequence, as we will see, of entanglement. Here is an assumption that is special to non-relativistic quantum mechanics. In non-relativistic quantum mechanics, the algebra E greater or equals to 0 is isomorphic to the algebra of all bounded operators on a Hilbert space H naught that sits inside the Hilbert space H of the system. That means that, of course, all the other algebras E greater or equal to T are also isomorphic to algebras of bounded operators on a Hilbert space. And that means, and states on an algebra of bounded operators on a Hilbert space, states are given by density matrices. So the states on the algebras E greater or equal to T in the non-relativistic setting are density matrices. If I know the initial state, let's denote it by omega naught, I can ask what will be the state of an averaged over a large ensemble of systems that are all prepared in the same initial state at time t. Well, that's simply the initial state omega naught restricted to the algebra E greater or equal to T. And since E greater or equal to T sits properly inside E greater or equal to 0, this restriction is, of course, non-trivial. So in the Schrödinger picture, the trace of omega t times x is defined to be the trace of omega naught, and you move x into the future from the initial time 0 to time t. All right. Now it turns out that this particular assumption that is specific for non-relativistic quantum mechanics has an interesting implication. The state omega at time t is obtained from the initial state omega naught by applying a semi-group of completely positive linear maps. The generator is what is called a Lindblad generator. Now here is a sort of a very basic idea, and that's the state reduction postulate. The states at all times t positive of any individual system in this ensemble of isomorphic systems, satisfying the assumption that we had on the last slide, this assumption for non-relativistic quantum mechanics. These states are given by density matrices proportional to finite rank orthogonal projections, in particular to rank 1 projections in the case they are pure. The projections pi t are random objects. They are obtained by unraveling the Limblad evolution of equation 4. Now, what unraveling means, I have to explain, and this will be the contents of section 4. The choice is the probability for choosing specific projections pi of t are given by a generalization of the Born rule. The new elements of the ETH approach to quantum mechanics as compared to standard textbook quantum mechanics are the ingredients 3 that I defined. That's this principle of diminishing potentialities. And then by ingredient 4, namely the proper definition of what the state of a system at time t is. And finally, the state reduction postulate. And these new ingredients have far-reaching consequences. For example, I think the measurement problem that bothers people completely disappears. It becomes a no problem. The information paradox disappears and so on. So I tend to think this formulation of quantum mechanics has some interesting features that deserve to be taken seriously. So here are the models that I will look at. We will consider systems that consist of static atoms. I will neglect the orbital motion of the atom, and these atoms should have finitely many internal states, say capital N internal states, and these states correspond to a complete orthonormal system of eigenstates of a matrix H sub A, which is the Hamiltonian of the atom. The atom is coupled to the quantized electromagnetic field. Given a pair of internal states ij, one specifies a transition amplitude E sub ij for a transition from state psi I to state psi j. And this transition is accompanied by an emission of a photon if the energy of psi I is larger than the energy of psi j, and it is accompanied by the absorption of a photon if the energy of psi I is smaller than the energy of psi j. The state space of the photons is the usual Fock space. In textbooks, the dynamics of the atom coupled to the quantized radiation field is described by unitary evolution on the Hilbert space that is the tensor product of the atomic Hilbert space little h sub a and the Fock space f of the photons. And the Hamiltonian has the following form. It is a sum of the atomic Hamiltonian, field Hamiltonian HF, and then an interaction Hamiltonian that couples the atom to the electromagnetic field. It is prefaced by a coupling constant E, which has something to do with the elementary electric charge. So, let me see. No, it's good. So, Hi is an operator that is completely determined by the transition amplitudes, Eij, that I introduced on the last slide, and that describe the interactions between the atom and the radiation field. What means either these systems in a non-relativistic regime? It means that we let the velocity of light, c, tend to infinity. In this limiting regime, the models described here perfectly fit into the formalism of the ETH approach. If the velocity of light were finite, we would have to also describe matter in a relativistic fashion in order for the systems to fit into the ETH approach. And of course, relativistic QED is a difficult theory, which I'm not going to consider in this talk. In any event, in the non-relativistic regime, where the velocity of light tends to infinity, the algebras E greater equal to T that I introduced, these algebras of potential events happening at time T or later, are isomorphic to algebras of the form bounded operators on the tensor product of the atomic Hilbert space H sub A, tensored with a certain subspace F greater than T of Fock space, which you obtain by applying arbitrary electromagnetic field operators localized at times greater or equal to T to the vacuum. It is then pretty easy to show that the principle of diminishing potentialities that I introduced in the last section holds in this model. We now suppose that at the initial time t naught equals 0, the systems S are prepared in a state without any photons. That means that the radiation field is in its so-called vacuum state. In the limit where C tends to infinity, the state of such a system restricted to the algebra E greater equal to T with time t greater than 0 is then always given by the tensor product of an atomic density matrix omega t with the projection, the orthogonal projection onto the vacuum state of the radiation field. And that holds for all times t. It's easy to understand why this is so. This is because if the velocity of light is taken to infinity, any photons emitted at some times smaller than t have already escaped to spatial infinity at time t. And therefore, in any bounded region of physical space, the state of the radiation field will look like the vacuum. This fact allows us to entirely get rid of the degrees of freedom of the radiation field, assuming that the systems are prepared in the vacuum state. We could prepare them in more complicated states of the radiation field, and that is actually of interest. But in this talk, I will always prepare them in the vacuum state in order to avoid various complications. So let omega naught be the density matrix describing the initial state of the atom at time 0, then the ensemble state of the system, namely the average of states of systems isomorphic to S over a large ensemble of identical systems at time t is obtained by restricting this initial state omega naught tensored projection onto the vacuum to the algebra A greater equal to T, and this ensemble state is given by a density matrix omega T tensored with the projection onto the vacuum. And as I explained, or as I claimed in section 1, the evolution equation for the atomic density matrix is given by a Limplatt equation. And in the models that we are looking at, the Limplatt operator has the form, it's a commutator term that describes sort of the unitary part of the evolution, and then a Limplatt term that describes the dissipation. The dissipation is due to the emission of photons. And the coupling constant in front of the dissipative term is simply the square of the elementary electric charge, denoted by alpha. The operators Vk that appeared in the dissipative part of the Limplatt generator can be calculated from the transition amplitudes for transitions between internal states of the atom, and from the form factors of the photon emission and absorption operators that appear in the interaction Hamiltonian H sub I of these models. Now it will turn out that the evolution of an individual system, isomorphic or identical to S, will be obtained by what one calls unraveling the Lindblad evolution. And I will have to explain what unraveling of a Lindblad evolution means, and that's the contents of section 4. Now, in order to prepare the ground for unraveling the Lindblad evolution, I will actually briefly sketch a simpler example, namely the example of unraveling the discrete diffusion equation on a lattice by the theory of simple random walk. And that comes in the next section. I won't spend too much time on that, otherwise I'll go heavily out over time. So let's look at the large ensemble of identical non-interacting random walkers on the simple hypercubic lattice. An ensemble state at time t for this system is given by the density rho sub t of random walkers on the lattice. The time dependence of rho sub t is governed by the diffusion equation rho dot t of x is equal to diffusion constant capital D times the discrete Laplacian delta applied to rho t at the point x. And the discrete Laplacian is defined in the right-hand side of this equation 6. The diffusion equation is a linear deterministic evolution equation for the ensemble state rho t. It is the analog of the Lindblad equation 5 that we saw on this slide at the bottom. All right. A solution rho t of the diffusion equation is non-negative for all times t, provided the initial condition is non-negative. That's a consequence of the fact that the heat kernel is positivity preserving, and furthermore, the total number of random walkers, sum over x, rho t of x, is independent of time t. Easy to check. We can normalize rho t such that the sum over all x of rho t of x is equal to 1 for all times t. You would like to understand what kind of stochastic motion of a single random walker omega implies that the time dependence of an ensemble state rho t is determined in addition to rewrite rho t equals rho of x of x times dt plus an error term of order dt squared. So when you let dt as approach 0, the error term disappears. What is the ontology of random walkers? The true state of an individual random walker omega at an arbitrary time t is a site x sub omega of t in the lattice, corresponds to a pure state, which is a delta function concentrated at the site x sub omega of t. This is really a pure state in this model. During a time interval t plus dt, a random walker omega may either remain at the site where it sits at the time t, or it may jump to a nearest neighbor site y, which means that it's the pure state delta sub x omega of t might either remain where it is in this interval from t to t plus dt, or it may jump to a state delta sub y, where y is the nearest neighbor of x omega of t. Several jumps do not appear if dt is very small, so you only have to consider either 0 jump or 1 jump. So we can now rewrite the equation, the diffusion equation in the form 7 by making the action of the Laplacian, of the discrete Laplacian, explicit, and then it looks like this. Rho of t plus dt is 1 minus twice the diffusion constant times the dimension of the lattice times dt applied to rho t, plus the sum over all nearest neighbors of x, diffusion constant times dt times rho t of y. up to error terms of order dt squared. So this, of course, implies that the state at time t plus dt is a convex superposition of pure states corresponding to sites x sub omega of t, that's the site where the random walker arrived at time t, and nearest neighbors of this site. The coefficients appearing in this convex combination of pure states can be interpreted as probabilities. If dt is tiny, rho t plus dt is then apparently given either by the pure state delta sub x of omega t or a pure state delta sub x of omega t plus delta. Delta is a jump to a nearest neighbor. The first choice, delta sub x of omega x sub omega of t, has probability 1 minus twice the diffusion constant times the dimension of the lattice times dt, and the probability of jumping to a nearest neighbor has probability diffusion constant times dt for all 2 new possible jumps. That, of course, means that the probabilities of not jumping or jumping to a nearest neighbor add up to 1. From equation 8, you immediately conclude that the probability for not jumping in an interval of times from time t prime to time t double prime is given by e to the minus 2 nu d times t double prime minus t prime. So what we are finding apparently is that the stochastic process that describes the dynamics of a single random walker is a Poisson jump process. And so this is, explained a little further here. In other words, the unraveling of the diffusion equation on a lattice is given by a Poisson jump process that describes the dynamics of an individual random walker. Now we want to draw inspiration from this simple example of diffusion on a lattice to unravel the Limblad dynamics in quantum mechanics and find the associated stochastic process. So we consider a system as in section 2, which is prepared at time 0 in an initial state omega naught tends at the vacuum. Let's suppose pi naught is a pure state, then omega naught is a pure state. In other words, it's given by a rank 1 orthogonal projection. I recall that in the Schrödinger picture, the ensemble state at time t is then given by a density matrix omega sub t times projection onto the vacuum. And the equation for omega of t, the evolution of omega of t, is given by the Limblad equation. That means that omega of t plus dt is equal to omega sub t plus the Limbladian applied to omega sub t times dt plus possible error terms of order dt squared. And the Limbladian is the one that I described in section 2, where I introduced the models. So according to the ETH approach that I sketched in section 1, the state of an individual system isomorphic to S is then given by pi t tensor the projection onto the vacuum, where pi t is a certain orthogonal projection of finite rank at all times t. That is a consequence of the state reduction postulate that I introduced in section 1. So let's try to find the stochastic process that describes the pi sub t projections. Let's assume for simplicity that pi sub t is a pure state, in other words, a rank 1 orthogonal projection. Then the state at time t plus dt, when averaged over a large ensemble ES of systems, all identical to S, and all prepared in the same pure state, pi sub t tensored with the vacuum, is given by a density matrix omega sub t plus dt tensored times the vacuum for the radiation field, where omega t plus dt is pi t plus the Laplacian applied to pi t times dt plus terms of order dt squared. This state omega t plus dt isn't pure anymore. Since omega t plus dt is a density matrix, it is self-adjoint and is positive, and it has trace 1. So we can actually apply the spectral theorem, and we can write omega sub t plus dt as a certain convex superposition of orthogonal, disjoint orthogonal projections, the spectral projections of the operator omega sub t plus dt. The coefficients of these projections are the eigenvalues of the density matrix, and they can be interpreted as probabilities. Turns out that pi super naught sub t plus dt is the spectral projection close to pi t. It has a probability or an associated eigenvalue that is of the form 1 minus order dt, and the other eigenvalues or probabilities p super delta are small, they are of order dt. And the sum of the p's corresponds to the trace of the density matrix omega sub t plus dt, therefore equal to 1. So, according to the state reduction postulate, one of pi super delta sub t plus to be chosen, and it's chosen random, and the probability form rule. In other words, the probability or frequency that the projection pi super delta sub t plus dt is chosen given that the initial condition at time t is given by pi sub t. This probability is given by p super delta of t plus dt, where p naught is the node jump probability. In order to come up with explicit expressions for these quantities, we apply something that I call infinitesimal analytic perturbation theory. This is a form of perturbation theory that should be in all the books, but I think is none of the books, which I find a little bit surprising. It goes as follows. Suppose H naught is an unperturbed operator with a simple eigenvalue E sub naught that is separated from the rest of its spectrum by a strictly positive gap. Let pi be the projection onto the eigenvector psi naught of H naught that corresponds to the eigenvalue E sub E naught. Let V be an operator on Cn that is a perturbation, and we consider the perturbed operator H of epsilon given by H naught plus epsilon times V. Epsilon will turn out to be dt in our application, so its concept is very, very tiny. We are interested in formulae for the eigenvalue E naught of epsilon of the operator H of epsilon that grows out of the unperturbed eigenvalue E naught, and for the corresponding eigenprojection pi of epsilon onto the eigenvector of H of epsilon corresponding to the eigenvalue E naught of epsilon. Well, this is something that everybody knows. You can introduce a certain antisymmetric operator S given by this formula 12, which I don't have to go into, and then the perturbed eigenvalue is given, E naught of epsilon is given by E naught plus epsilon times the expectation value of the perturbation V in the unperturbed state of H naught up to errors of order epsilon squared. And the projection onto the perturbed eigenstate is given by the original projection pi onto the unperturbed eigenstate minus epsilon commutator of this operator S with pi up to terms of order epsilon squared. Now, since epsilon will be dt in our application and dt will approach 0, it turns out that first order perturbation theory will be exact. The equation for E naught of epsilon given in equation 13 is what people sometimes call Feynman-Hellman theorem. Of course, it was already known to Rayleigh and Schrödinger. And pi of epsilon is the first order Rayleigh-Schrödinger expression for the perturbed eigenprojection. Now, if you want to apply this to perturbative problems in quantum mechanics, you would have a unperturbed operator H naught and a perturbed operator H sub 1, say, and you now connect the unperturbed operator to the perturbed one by a family, a differentiable family of operators H sub t. T varies between 0 and 1. This family should be continuously differentiable, and you can now find the spectrum and the eigenvectors of these operators ht by solving an initial value problem consisting of a system of ordinary differential equations, which can be equations. This is a very clever and useful variant of perturbation theory, especially in situations where you have eigenvalue crossings and the like. And it's strangely enough, I think it's not in the books. I call it infinitesimal perturbation theory. We now apply it. So, I go back to the Limplatt equation 10. And I use infinitesimal perturbation theory to derive a system of ordinary differential equations for the eigenvalues p sub no jump t and the eigenvalues p super delta t, t plus dt, and for the corresponding eigenprojections pi super delta sub t, t plus dt. I said in the general equations for infinitesimal perturbation theory, I said H naught equals to pi sub t. It's a projection, a rank 1 orthogonal projection. And the perturbation V is the Limplatt generator applied to pi sub t. And the coupling constant epsilon is equal to dt. For this joy, an eigenvalue 1, which is simple, and an eigenvalue 0, which is n-1 fold degenerate. Now we can apply equation 12 to define this anti-symmetric operator S. It's given by formula 14, which I don't have to look at in detail. It's a well-defined anti-symmetric operator. And then I can use the equations of infinitesimal perturbation theory and get the following things. The eigenvalue p no jump, which is really the analog of the eigenvalue E naught of epsilon in equation 13. This eigenvalue is given by the Feynman-Hellman theorem. Well, the unperturbed eigenvalue is 1. That's the eigenvalue 1 of the projection pi sub t. And then there is an expectation of the perturbation, which is L sub alpha applied to pi t in the unperturbed eigenstate, which is given by the projection pi sub t. And everything multiplied by dt, and then there are further corrections of order dt squared. And of course, if I take the logarithm of this equation, I see that logarithm of p no jump by dt is actually trace pi t times L sub alpha applied to pi t, which you can easily show is always smaller or smaller or equal to 0. That means that when you integrate this equation, you get the probability for no jump between 2 times 0 and t is given by some exponential, which is always smaller than 1. This formula would be wonderful if we knew the equations for the projections pi sub s at intermediate times s between 0 and t. Well, we now have to find the equation that determines these projections pi sub s. And that comes on the next page. By using the second equation in 13, I get a differential equation for the eigenprojections pi sub t in the absence of quantum jumps, namely the projections that correspond to the eigenvalues little p sub no jump, namely the differential equation is given by d pi t dt, the derivative of pi t with respect to time t equals 1 minus pi t, which I denote by pi t perp, times L alpha applied to pi t times pi t plus the Hermitian conjugate. This is a system of nonlinear cubic differential equations for these projections pi sub t that describe the state of the atom in the absence of quantum jumps. What about quantum jumps? Well, the quantum jumps might appear jumping from a projection pi t to some of these projections pi t super delta. And these jumps have small probabilities. The probability of jumping to a new branch, so to say, in the time interval from t to t plus dt is always proportional to dt. And these probabilities p super delta can be computed by diagonalizing a certain finite dimensional matrix. Now you could ask what happens if the perturbation in the Limplot generator that describes the dissipation were absent, namely if alpha were 0. Well, then it turns out that p no jump then one, and it turns out that this general equation that becomes a linear equation. The time derivative of pi t is given by minus I commutator of the atomic Hamiltonian with pi t, which is the usual Schrödinger von Neumann equation. So describing unitary evolution. So the deviation from this unitary evolution without quantum jumps is entirely due to the dissipative terms in the Limplot generator. We could now introduce an analog of the Wiener measure of Brownian motion on the space of trajectories of individual quantum systems. For example, we can suppose that the state of an individual system isomorphic to S exhibits quantum jumps at times t1 up to tn. And I want to follow the evolution of the system between time 0 and a certain final time t fin. The state evolves continuously for all times between two jump times, according to the differential equations that we had derived here in this box, point 2. But at time between tj and tj plus dtj, there is a jump from a projection that evolved continuously to a new projection disjoint from the one that came in. And we can now specify trajectories which have these properties and compute their probabilities. I'm not going to do the details here, otherwise we will run out of time. But you can, from what I have said so far, you can compute these probabilities, and that defines something like a Wiener measure on the space of quantum trajectories of individual systems. Turns out, when you look at this Wiener measure, it looks like a Poisson process, but the probabilities of jumping in this Poisson process have to be computed by solving nonlinear equations and then doing an integral. Is fairly complicated. I think it's a process that mathematicians have not really investigated so far, but what I said in this section provides all the elements to investigate these processes with in arbitrary detail. I hope this was more or less clear. I think the basic ideas are to apply the postulates of the ETH approach, then using infinitesimal perturbation theory to compute how the node jump probabilities evolve and to compute the jump probabilities. And then you get this analog of the Wiener measure that is here specified in equation 16. So this is a sketch of the general theory of these quantum Poisson jump processes. These processes would become a little more complicated if the radiation field had not been prepared in the vacuum. If you prepare it in a state that describes photons appearing at different times, then all these expressions become somewhat more complicated. Not so difficult to figure out what the generalization is, but I will not go into this today. Now we look at the simple example, and that's the example of a two-level atom. So if you look at the two-level atom, you can describe the states of the atom by 2x2 density matrices. Maybe I should show them. Sorry. The 2x2 density matrices are of the form 1/2. The identity matrix in 2 dimensions plus sigma. Sigma is the vector of Pauli matrices, and n is a vector in free space of length smaller or equal to 1. All 2x2 density matrices of this form. In this case, you can describe the stochastic of an equal to level as an evolution of these vectors n of t. And for a pure state, n of t will be a unit vector. It will be a vector on what is called the Bloch sphere. And so what you're trying to find out is the law that describes the dynamics of an individual system in terms of a trajectory of unit vectors on the Bloch sphere, which occasionally will jump from where they land at some time t to the antipode. That's really the Poisson process that appears in the two-level case. It's a process that describes a nonlinear evolution of vectors on the Bloch sphere that occasionally at discrete times jump from where they are to the antipode of the Bloch sphere. So I assume the atom has a simple atomic Hamiltonian. It's a 2x2 matrix. H bar omega is the energy difference between the ground state and the excited state. And then the state, as I mentioned, the states of the atom are described by this density matrix. Matrices omega of n. Omega of m plus omega of minus n is always equal to the identity. I introduced lowering and raising operators, sigma minus and sigma plus, and then the Limplot operator in this simple example, in case the radiation field is prepared in the vacuum state, is given by minus I h bar inverse commutator of atomic Hamiltonian with omega plus alpha sigma minus omega sigma plus minus 1/2 anti-commutator of the density matrix omega with the 2x2 matrix sigma plus times sigma minus. The Limplot equation can be written as a linear equation for the vector n that appears in the density matrix. And as long as I look at the Limplot equation, which describes the evolution in vector n will shrink typically. So it will dive into the interior of into the Bloch ball, if you like. The equation is given here in equation 20. And now, if you look at this equation, you will find out that any solution of equation 20 will converge to minus E3. That's the unit vector that corresponds to the ground state of the atom as t tends to infinity. That is because eventually the atom will emit a photon, and since the radiation field is prepared in the vacuum, once it has emitted a photon, it will remain in the ground state. Now, I assume that the atom is in a pure state at time t, described by a unit vector n of t. I would like to compute the vector in the Bloch ball at time t plus dt that is predicted by the Limplatt evolution 20. I denote it by n bar of t plus dt. It's given by n of t, and then there is a term describing precession of the vector n of t around the vector E3, the unit vector that points up. And then there are dissipative terms. Now, if you apply the principles of the ETH approach, then you will say that M bar should be a convex combination of pure states, and these pure states are given, I denote them by n of t plus dt. One of them is given by n bar divided by the length of n bar, and it has probability p no jump, and another pure state appearing in the convex combination of n bar is given by minus n bar divided by the length of n bar, and this has a probability p flip. And these probabilities can be computed. P no jump is 1 plus m bar t plus dt divided by 2, and p flip is 1 minus n bar divided by 2. And obviously the sum of not doing a jump and or a flip and the probability of doing a flip equals 1, as we would expect. And now you can start to solve these nonlinear equations that I derived for you in the last section. Here, this equation in the box. In the special case of the two-level atom, these equations have very specific forms. For example, 23 is the nonlinear equation for the three component of the vector n of t in the absence of flips. And it can be solved. It's a cubic equation. It can be solved. And then you can reconstruct the entire vector n of t from its third component, simply by taking into account the precession around the three axes. All right. Turns out in this case, the probability that the atom doesn't jump from the excited state to the ground state is exponentially decreasing in time. In fact, equal to it remains equal. It's identically equal to 1 if I prepare the atom in the ground state, and if the atom is prepared in coherent superposition of the excited state and the ground state, then it's a little more complicated. The probability for no jump is given by a certain fairly explicit formula. It's of the form exponential minus lambda t, where lambda t is given by a certain integral that you can evaluate totally explicitly. So then we can compute the probabilities of state trajectories of two-level atoms with flips at certain discrete times tm plus dtn. N goes from 1 to anything, and it is treated as in section 4. 3 should be 4 on top of this transparency. So for sufficiently large time, after finitely many flips, the atom will always be found in its ground state. This would be different if we included Rabi oscillations of the atom. That's an interesting case too. We have worked out the details for Rabi oscillations. And in fact, I think, the discussion of the nonlinear equations that describe the dynamics of these atoms in between two quantum jumps, the discussion of these nonlinear equations is a very interesting problem that should be addressed in quite some generality, because I think very interesting phenomena will be encountered. So I now conclude and just go over time for 2 or 3 minutes. In idealized models of systems charged matter interacting with the quantized radiation field, described here in the limit where the velocity of light tends to infinity, the principles of the ETH approach to quantum mechanics apparently yield totally explicit predictions concerning the stochastic time evolution of states of individual systems. I do not have to put in any handmade mechanism as, for example, in the Girardi-Rimini-Weber approach, the stochastic process that describes the stochastic time evolution of the states of individual systems comes out completely uniquely from the basic postulates of the ETH approach. The stochastic process is what I call a quantum Poisson jump process. I've tried to sketch what these processes are. I think they should be studied in more detail now. I think you will really encounter rather fascinating phenomena by considering the properties of these jump processes. It would be interesting to test the fine print of these predictions in experiments. I'm not an experimentalist, I'm a retired theorist, so I hope at some point some younger experimentalists might get interested in testing some of our predictions. And of course, we are also interested in the relativistic version of this entire story. I have started to work it out. There are 2 papers where there is a sketch of the relativistic ETH approach, but I cannot go into that today. I think it will deserve to be worked out in more detail in the future. I would like to thank you for listening, and I'm happy to take as many questions as you can possibly ask in 1 hour.
Okay, great. Thank you, Jürg, for a very clear and deep lecture. It certainly is an eye-opener for me. I'm still trying to process. So the talk is open for questions, please. Go ahead if you have a question. You can just use the icon to raise your hand.
You can also, express criticism, or you can tell me that you didn't understand what I was talking about. Whatever you like, don't be shy.
Yeah. So you don't introduce any new fundamental constants of nature,
No.
unlike GRW.
Absolutely, that's right.
And then how do we get the so-called GRW amplification process? That the quantum jump process should be, let's say, if I'm correct, negligible for microscopic systems, but significant for macroscopic ones.
So, I mean, in my case, the quantum jumps do not happen because there is no mechanism that forces the system to jump. It comes out from this principle of diminishing potentialities, that the algebra of what might happen in the future after time t becomes smaller and smaller the larger time t. And then I assume that in spite of algebras being smaller and smaller, the state of an individual system should always be pure at every time t. This immediately introduces the stochasticity of the evolution of individual systems.
Okay.
So
and,
you
and
don't need any new constants of nature. You have to understand why the algebras of events that might happen at time t or later, why these algebras shrink with time t. And that is a consequence of Huygens principle. Namely, if you couple charged matter to the radiation field and these photons that escape before they are detected, then these photons will never come back to the system. They speed away at the limiting speed. And if you didn't measure them when they were emitted, unfortunately, you can never know the information they took away. That's Huygens principle. More mathematically speaking, if you take the two operators that describe the electromagnetic field tensor, you evaluate them at 2 points x and y in Minkowski space, and you compute the commutator. The commutator vanishes unless the 2 points can be joined by a light ray. That's the mathematical expression of Huygens principle. This principle immediately implies that these algebras E greater equal to T become smaller and smaller as T increases. So that would also be interesting to explain.
Okay. Yeah, I have a
And
very
everything
naive
in your mind.
question. I have a very naive, it's not really a physics question. You probably discussed this with Girardi. So I'm puzzled now. I mean, it's very naive. How come GRW got so much more prominence and coverage compared to ETH? I'm really trying to understand.
This is there is of course a simple explanation. You know, when I was an active professor, I decided I can only think about quantum
Sorry, your
as
noise
a
is.
hobby. And in fact, I
Okay.
thought a lot about quantum foundations ever since the early 90s, but I never published anything because my PhD students would have worried that they cannot have a good career if they work on quantum.
Yeah,
So I had
okay.
to do more pragmatic things. But then when I retired in 2011, I decided now it's the time to think about quantum foundations. And by about 2014, I had all the basic ideas for the CTH approach. And then I started to publish some papers, but that's of course after GRW. And strangely enough, probably I haven't written my papers very well. I guess Felix should have helped me. He might be a better writer than I am. In any event, it seems to me that the community hasn't really understood very well what I have done so far. And so at some point, we should probably write a very pedagogical summary of the CTH approach.
Yeah.
And then perhaps it
Yeah.
will start to...
I'll definitely think about it because I have spent time on GRW, but now I'm asking myself, why should I not prefer this? But I mean, I'm still thinking what's going on here. So is it, can I say that the GRW stochastic noise field is replaced naturally by the electromagnetic radiation field in your work?
Exactly. You know, in order to get stochasticity in quantum theory, you need degrees of freedom.
Your voice is breaking, Jürg. Could you kindly repeat that sentence?
Mode. Pardon?
Could you kindly repeat the last
As
sentence?
soon as, yes, I will repeat it. In order to get stochasticity in the evolution of a quantum mechanical system, you need degrees of freedom that correspond to massless modes. There may be other mechanisms that guarantee this principle of diminishing potentialities, but the easiest, most obvious mechanism is that degrees of freedom of your system are coupled to massless modes. That automatically basically introduces stochasticity into the evolution of individual systems. And this is, I think, something that, was really a new observation that I made. And it's, who knows, maybe Felix had similar observations. He might comment on it if he's still awake.
Felix, you want to say something?
Yeah, sure, I'm still there.
Yes, so maybe you
Yes, I
had
mean,
somewhat similar ideas.
yeah, I agree with you. Also, like in this collapse model, which Claudio and Johannes Kleiner and me just developed, it's a bit similar that also this kind of waves propagating with the speed of light, this is what triggers the collapse. Although the the mathematical formulation of this mechanism is quite different.
Yes. I think there's also a question by Mr.
Yeah, Bernd,
somebody.
go ahead, please. Bernd, go ahead, please.
Thank you very much for this wonderful talk. I have to admit I'm on the side of the people who would ask some basic question of understanding. I hope you don't mind if I do this. I have difficulty understanding how the nonlinearity comes into your model. You start with self-adjoint operators, you start with projection operators, which are also self-adjoint, so linear. I have not completely understood how the nonlinearity gets into your formalism and also what physically introduces the nonlinearity. Can you please help me?
Absolutely. I can.
Is he frozen again, or is it only on my computer?
Explain that. So, you see, thanks to the presence of massless modes, the evolution of an ensemble state, namely of an average state, when you take the average over a large ensemble of evolution is given by a Lindblad equation. The Lindblad equation is linear and deterministic. But it has the following feature. When you feed in a pure state at some time t, and you look at the resulting ensemble state at time t plus dt, it is a mixture.
Okay, so you evolve a pure state
and
into
the postulates of the ETH approach. Sorry?
Sorry, I have some trouble. Sometimes you're interrupted.
That's probably that. I mean, my internet connection appears to be fine.
Maybe it's on my side.
Yeah, so several of us had noise. I don't know whether it's
But,
at the
maybe sometimes it might be unstable.
yeah,
So-
maybe at the Zoom at Bristol or London. I don't know where the problem is. There seems to be some problem today.
I see.
Okay.
Anyway, let me try once more.
Yes, sorry.
You feed in a pure state at time t. You let it evolve according to Lindblad to time t plus dt. The resulting state is not pure anymore. So you decompose it into pure states. The pure states are simply the spectral projections of the ensemble state omega sub t plus dt. And now the state reduction postulate of the ETH approach says that this state, the one of the spectral projection 11. Now, the probability of choosing pi naught, which is the projection close to the initial projection pi sub t, the probability of choosing pi naught is large. It is of form 1 minus order dt. And I call this probability p sub node jump t plus dt. Now we have to calculate p sub node jump and we have to calculate pi naught. Well, this is done by perturbation theory. But you see, perturbation theory automatically when you compute the perturbed spectral projection corresponding to the largest eigenvalue, well, it is given by an equation that is nonlinear, and it comes on the next transparency. One. You know, the time derivative of pi t, when you choose it, that I just repeated, is given by a certain right-hand side, which is non-linear in pi sub t. That's just applying infinitesimal perturbation theory.
Okay, so the nonlinearity comes out of the perturbation theory, correct?
Absolutely.
Okay, thank you.
Perturbation theory is used in order to calculate the form of the projection that belongs to the largest eigenvalue of the density matrix omega sub t plus dt. This
Hello?
there, everything is much simpler, but in this case, for the quantum Poisson process, you really have to solve these nonlinear equations.
Okay.
It's one, and then from once you have solved this nonlinear equation in point 2, you can use abilities that are not, the jumpers are given them by diagonalizing a certain n-1 by n-1 matrix. Now, if you hear this the first time, you should not be surprised that you don't understand the details, because it actually took me a rather long time to figure this out. But now, since it has been figured out, if you read one of my, I have a joint paper with Joe Gang and Alessandro Pizzo about these formulae, and when you study it, you will see it's not very difficult. It can certainly be understood.
Okay,
The
then I will
point
look.
is, you see, there is a very strange, wrong idea in the community, and it's the following. It says that the evolution of the state of an individual system is given by the Schrödinger equation as long as there is no measurement. But when there is a measurement,
We lost you. Could
to
you
the range of a spectral projection of the quantity. Pardon?
the
Repeat.
second sentence? So you are saying that the statement that the evolution is Schrödinger evolution until a measurement is made needs to be qualified.
Absolutely. It's just, I think it's a very naive idea. And you see, Schrödinger was an intelligent man. He developed many of the mathematical tools we use to solve problems in quantum mechanics. But he's responsible for introducing the most abominable confusion into quantum mechanics. And that was that the evolution of the state of a system is given by the Schrödinger equation. That is simply not true. As soon as you look at the system that
Yeah, we are losing you at
the system is
important
not given by
points.
the Schrödinger.
Can you repeat? Say, as soon as you look at the system, after this we
As
lost
soon as
you.
you look at the system where matter is coupled to massless modes, the state of such a system, of an individual system of this type, does not evolve according to a Schrödinger equation. It evolves according to one of these quantum
Now we've lost again.
systems.
You think Schrödinger was not aware of this, is it, to your understanding?
No,
Could
he did not understand. He made a big mistake. He thought that his Schrödinger picture was the right picture, and the Heisenberg picture and the Heisenberg evolution of operators was inconvenient. But in fact, physics-wise, the Heisenberg evolution of operators is really fine and doesn't have to be modified at all. But the evolution of the states of individual systems is definitely much more complicated than Schrödinger thought. That's sort of inverts the fundamental message of this talk and of the entire you know, of the ETH approach that I have developed during
Yeah,
the
I think
past.
so. You are saying that what GRW proposed is in a sense already there within quantum mechanics.
Yes. It's of course not the same as GRW, but it is reminiscent of
Yes. Yes.
if you understand quantum mechanics properly, if you understand the physics at a somewhat deeper level that happened previously, that's sort of what the message is.
And you mentioned the fine print of ETH, which would show up in experiments. So would that distinguish it from conventional quantum mechanics?
So you see, for example, let me mention an example. Take an atom that you put into a cavity and you massage it by letting it exhibit Rabi oscillations. You can do that by putting the atom into a coherent, then it starts to oscillate. That's called Rabi oscillations. Every once in a while, such an atom will emit a photon. The emission of the photons happens at random times.
Mm-hmm.
Formalism I have developed and sketched here in this lecture
Lost you, sir. The formalism that you have developed
of
in
these
this
random
lecture.
times, the probabilistic law of these times.
Could you
The
repeat,
formalism
please?
developed in this lecture or sketched in this lecture enables me to predict the laws of the random times at which photons are emitted by an atom that
Okay. This is
this is
something.
something that in the standard formalism, you see in the standard formalism, this law is not computable. So
Yes,
it's
I
a
get your picture.
prediction. It's
I
a
get your
prediction
picture.
that I think one could try to test experimentally, and it is a little bit new.
I'm just curious, what would be the corresponding situation in Bohmian mechanics?
Bohmian mechanics is a totally different idea. You see, in Bohmian mechanics, there are no jumps. The evolution of the Bohmian particles is deterministic and non-linear, by the way.
Yeah, that's why I was
The,
thinking they should be able
the,
to predict when the photon will be emitted.
the Bohmians.
Yeah,
No,
I'm
but
just asking, I may be wrong.
the Bohmians have troubles describing photons.
Okay.
I mean, there is probably some mechanics that pretend to also treat the radiation field. But it's definitely a somewhat contract formalism. I have a lot of respect for the Bohmians because they put their fingers onto problems of quantum mechanics that were not well understood. They have proposed a mathematically consistent formalism for how to deal with these problems. However, in the end, I think Bohmian mechanics misses the physics of quantum theory. So I'm definitely not the Bohmian, and I do not believe that it is the right approach.
Thank you, thank you, thank you. More questions, please? I'm really enjoying the discussion. It's been very illuminating.
Probably everybody is now a little bit exhausted.
Yeah, there's a comment from Bernd. Let me see what he's saying.
Maybe Harry has a question or remark.
Okay,
No,
so
probably not.
Bernd's saying that it's fair to say that the Bohmians are the loyal opposition to quantum theory. I don't know, Bernd, what that means.
Sorry, no, I did.
Did someone else has a question?
you good. Well,
Yeah,
I'm sorry that apparently the internet connection wasn't.
yeah, but I think during the talk it was reasonably fine. We got what you were saying. I'm curious. ETH stands for, apart from the name of the organization, I think it stands for something else also, but I'm
So
forgetting.
it stands for Events, Trees, and Histories.
Ah, yes, I remember.
ETH
Felix-
formalism clarifies what an event is. It says that the possible evolutions of states of individual systems are trajectories on a tree-like structure, and and a specific trajectory is a history.
Yes,
So
yes,
that,
I remember, yes.
Of
Events,
course,
trees,
I
and
confess that I chose these initials because they reminded me of my home institute.
Yeah, why not? We have the Copenhagen interpretation, we have the Oxford interpretation, we have the Trieste interpretation. So now we have
all.
ETH.
Yes.
You have
But
the
you see, the
ETH.
ETH is not an interpretation. The ETH is a complete quantum mechanics.
I agree.
Quantum mechanics.
I agree, yes.
But people have been sort of misguided by always trying to come up with new interpretations. As already Dirac said, the problem with quantum mechanics was that in the way it was formulated, say in 1930, it was not in final form.
Mhm.
Then people also then trying quantum mechanics, they kept in reinterpreting what was already there. The really clever, one of them was Heisenberg and the other one was Dirac. So that's what I tried to do. Well, there would be many further things to say, but yes.
Sorry, Bernd, you're saying something?
I'm trying to say something that would be more
No,
fair.
I just said there would be many. Yes, please go ahead.
Okay, I hope it works better now with the
Go
connection also. Concerning your equation 2 on your slide at the moment. So the operator,
Yes.
I think it looks like an L. Maybe I misread it. This is a nonlinear operator, is this correct?
No. L alpha is the Limplot generator.
Ah, okay.
The Limplot generator is linear in its argument. It's linear in the pi t.
Okay,
But
okay. Good.
Tm from the left by pi t perp, and then there is the Hermitian conjugate term that needs to be added. So in the end, when you do these multiplications, you get something that is second or third order in pi t.
Ah, okay, good. Thank you.
And you know, these equations.
Sorry, could you please repeat that? The connection broke.
To describe fairly complicated behavior. Sorry?
No, it's okay. We got you. Yeah. Okay. Thanks, Hari. Yes.
There is also a chat.
Yeah, no, that's Hari thanking you for a wonderful talk.
Oh, okay.
So, any particular paper?
Apparently, the Bromians are.
I was asking any particular paper or review you would recommend we go and read on ETH. I see that you have a 2020.
I have written a review paper which will appear in an Encyclopedia of Mathematical Physics, published by Elsevier. It's a very painful story because I still haven't received the page proofs, but the preprint exists. I can send it to you. Send me an email. Whoever wants to know more about what I've been talking about will receive 2 or 3 either published papers.
What I'll do, I'll do this, Jürg. I'll write to you for references, and then I'll share it with a mailing list, and whoever is interested can look it up. We have a mailing list of.
Absolutely. I think that's a good idea.
Yeah, I'll
All
do
right.
that. Write to you tomorrow and ask for
And you
reference.
know, some of the papers you find on archive, of course, on the Los Alamos archive.
Yeah.
But I think this review that will be published in the encyclopedia was never uploaded.
Okay, that will be great because that will be
So I can
complete
send it
and
to you.
comprehensive. Yes.
I think it's very readable.
Yeah.
Yes.
Great. All right. Anything more?
I'd like
Anybody?
to thank you for.
Yeah. Do you
It's
think you?
certainly been a pleasure to be this lecture, and I hope
Yeah.
that
Could you kindly stop sharing your slides for a moment? Then we can come full screen, I think.
absolutely, yes.
Yeah, great. Good to see everybody
Very good.
on screen. And so once again, thanks for a very, very, very wonderful and deep lecture. So friends, after 2 weeks also, we have a very interesting talk by George Sparling. I think he was a student of Roger Penrose. And the talk is titled Space-Time is Six-Dimensional and the two extra dimensions are time-like. So I think that would be very
yes, that's very interesting, but it's a very dangerous thing to have more than one time-like dimension, because then
I agree. So I think my way out is to say
condition will go out.
my way out is to say that these three so-called time-like dimensions are actually coordinates on the same footing as the spatial coordinates. The role of time, the real thing that is time that flows, is played by something else.
I see. Well, I look forward. I may, if I have.
Yeah, I have you on the mailing list. I'll keep you posted. Yeah.